Sorry? Okay.
Yeah. All right, so Oded will tell us about non-commutative Grothendieck and what it is.
Okay, good morning. It's always fun to be back here, just to hear Avi calling me Oded, because no one else calls me Oded, but that's great. Yeah, I miss that. So,
I think they like that. I say, what do you prefer?
Oded, yeah. Oded. Everyone calls me Oded. Yeah. But that's okay. No, you should keep calling me Oded. Otherwise, I wouldn't come.
My brother is Oded.
I know. So I'll tell you about something we did recently with Joop Biet, who is now back in Amsterdam in CWI. He was a postdoc, and Rishi Saket was from IBM in India. And we are considering a problem, the Grothendieck problem. Thanks. And we'll show some tight hardness results for this. So let me start by asking you a trick question. What is the oldest semi-definite programming result that you know of? Okay. Okay. Yeah, good. Grothendieck inequality. It's not really. I mean, he didn't phrase it in terms of semi-definite programming. Lova's probably much closer, but in a sense, this is the oldest reference I know for things of that form, and also I think it's one of the nicest. So if I won't show you the way that you prove the SDP gap, but it's actually a very nice proof. There are lots of proofs here, and they're all very nice. What we'll do today is the other side of the coin. We'll do the hardness result. Okay, so this topic dates back to work of Grothendieck from 1953. A very celebrated work. Started the whole area of tensor norms, geometry of tensor norms, of tensor products of Banach spaces. Tensor norms is called. And incidentally, Grothendieck recently died. This was a few weeks after we posted a paper. No, I don't think we have anything to do with it. This area I started became very influential. He proved several things, and one of the main things he proved, that the main result he proved there is Grothendieck's inequality. It's known today as Grothendieck's inequality, and it says the following. We consider the following optimization problem. So you have a matrix M, say D by D, and you consider the maximum of absolute value of some Mij, say alpha I beta j, and you're maximizing overall alpha I beta j in a plus minus 1. So over all possible choices of sign, alpha I beta j, you're maximizing this thing, this bilinear form in the alpha and the betas, and you're trying to maximize it. Okay, so this is the question he considered. The reasons is something I won't mention. The reasons he considered it. For us, it's a natural optimization problem. It's related to things like max cut and other things. I'll get to it in a minute. What he wanted to do, he wanted to understand this better, so he wanted to do something else. Let me call this thing OPT. You might guess why. OPT of M. And he defined another quantity, which I'll call SDP. You might guess why. Of M, where I do the same thing, except I place these things by unit vectors. Okay, so I have a supernorm, some Mij, and then I take a inner product of Ai and Bj, and those are vectors of arbitrary dimensions. So those are unit vectors. So I also have a supernorm here over dimensions. Okay, so I have Ai, Bj, norm 1. Okay. Oh, I have to process it. Okay, so obviously this thing is only bigger because there's more freedom. Okay, one-dimensional vectors have plus minus 1 in them, but I allow arbitrary unit vectors. So obviously we have that. Okay, and the amazing thing that Grothendieck proved is there's a constant. Some universal constant, call it Kg, that also bounded from above. So this is OPT of M. Okay. So that's what he proved, and this is very important in function analysis, and it shows up in lots of areas. This is the inequality, and actually I should mention that the constant is actually not known. The optimal constant is not known. He proved it with some somewhat big constant, and this has been improved over the years. there was a very nice proof by Krivin, who showed that it's at most like 1.782. It's actually, this number is very nice. Some square root and 2's and pi's and lots of things in logs. So it's a natural number. It also came up with a very nice, elegant natural proof. And we expected it, well, many conjecture this is tight. But then in 2011, Braverman, Makarichev, and Nao showed that actually it's not tight. Actually, the constant is strictly smaller than that number, whatever number is there. So currently it's open what the best constant is. This will not worry us too much in this talk, but this is the situation. Now, what's the connection to us, to computer science? This came in the paper of Noga and Asaf. So this is Alon Nao in 06. And basically they did three things. Okay? So before that paper, I think people in computer science didn't even know about that inequality. And what they realized are three things. Where first they said, this RPT thing is actually interesting. It's an interesting optimization problem. You can do lots of nice things with it. You can compute cut norms of matrices. It's connected to statistical physics. So it's a nice optimization problem. You can see this is basically what it says. You have this matrix M, and you're kind of trying to partition the rows and the columns in a way that maximizes the imbalance between two parts of the matrix. And this shows up in many areas. It's related to max cut, as I mentioned. So it has some applications. It's a natural optimization problem. And they also realized that SDP-M, well, it's an SDP. Okay, so you can solve it efficiently. And that already tells you something. That tells you that, well, you can approximate this OPT. You can approximate the optimum to within a constant set. So SDP is semi-definite programming, and that's something we can efficiently compute. So it's a family of optimization problems we can efficiently compute. And you don't need it for this talk, but those are programs of the form. You have some, you want to maximize some linear combination of inner products of vectors of unrestricted dimension. So it's crucial that here, I didn't write it, but there's also supermum over dimensions. So we don't restrict dimensions of A and B. And just so happens that this is something you can efficiently, it's a convex optimization program. Okay, it's part of this family, and you can compute it efficiently. So this is the connection to computer science. Okay. So once you have these two facts, you already have efficient approximation algorithms for anything you can express in this way. They did the third thing, and the last thing they did is actually give an algorithmic rounding procedure. So, so they made rounding efficient. Let me just explain what this means. So when you want to prove such an inequality, the way you do it, you say, well, let's take a solution to this supermum. Take some vectors, okay, that achieves a big value here, and let me show that also OPT is big. Okay, and the way I do it, I take those vectors and do what we call round them. Okay, so we take the vectors and map each vector to either +1 or -1. Okay, so this is the rounding, what we call rounding procedure. So we take any assignment here to this SDP, any choice of vectors AI, Bj, and show how to map them. Usually it's a very nice way to signs alpha and beta. So there's the famous Gomez-Williamson rounding that uses some hyperplane cut to decide which ones go to +1 and which to -1. And then what you have to prove is that this preserves, or up to the factor kg, this preserves the value. And this is exactly what Krivin's proof does and Grothendieck's proof does. Is that clear? This is how you prove such an inequality. Okay, map the vectors to signs. And what they did is basically say, actually the way the proof, the mathematical proof that shows how to map this is actually algorithmic. You can actually make an efficient algorithm that takes vectors and maps them to signs. And the implication of that is you can not only approximate the value here, the maximum, but you can also output something, output signs ±1 that achieve close to the maximum by solving this semi-definite programming, recovering the vectors, and then mapping the vectors to signs. That's the picture. Okay. So this is it for the background on the Grothendieck inequality. Any more? Feel free to interrupt me. I don't have. Yeah.
About the hardness of this problem?
I will say. Definitely. Yeah. So I'll go back to hardness. Before, let me just talk about the topic of today's work, which is the non-commutative Grothendieck problem. So the name is unfortunate, at least I think for many people this would be quite intimidating. It's actually a very nice extension of this optimization problem. Basically, the word non-commutative just means that it involves matrices and not vectors as it is here. Before I get there, it's good to mention that if you think of this optimization problem mathematically, you can think of it as if you're trying to compute the norm of a bilinear form on L infinity cross L infinity. Okay, we're maximizing over vectors of L infinity norm at most 1. That's what it means that they have to be plus minus 1. And what we're doing here is maximizing the norm or computing the norm of a bilinear form on L infinity cross L infinity. This would be L infinity cross L infinity. Now, what we consider today is the non-commutative extension of it, non-commutative Grothendieck. And this is the interesting history. So it's an extension of that optimization problem. And it was already conjectured by Grothendieck himself in 1953 that it should, something like that should hold, such an inequality should also hold for the extension, for the non-commutative version. So you don't need to know exactly what it is, but let me just once just flash it. Okay, I cannot flash. I'm not using PowerPoint, but imagine I'm just showing it quickly. And basically, it's something like this. Instead of a bilinear form on 2 vectors, you have a bilinear form on 2 matrices. Okay, so you're trying to take you're taking the maximum of all sorts of matrices. You don't need it for this talk, but let me mention it anyway. So I have the maximum, and I have the sum. Now, it looks a bit ugly because there are lots of indices, but it's just a bilinear form. So AJ, B, KL, bar, and A, B are matrices. So there are D by D matrices that are unitary. So for convenience, I switch down to the complex case. Don't worry about this if you don't want to be bothered by it. Both this and that can be defined in a real and a complex setting. This is more natural. This version is historically always been investigated in a complex setting, and we'll follow it during this talk. Now, what is this thing? Well, basically, you can imagine you're trying to find 2 rotations. Unitaries are just the complex analogs of rotation matrices, orthogonal matrices. So you can imagine trying to find 2 rotations that maximize some goal function that is bilinear in the matrices. Turns out, this question is quite interesting for computer science, and let me mention it. There's also an SDP, which I'll spare you. I mean, you can write some SDP. It's actually a very interesting SDP. Maybe I'll say a word about it in a minute. I don't want to write it because it's a bit tricky to define precisely. But there's also, and the question is whether these 2 things are related. As before, Grothendieck conjectured that. Okay, so we still have OPT of T is at most SDP of T, and Grothendieck conjecture there's a constant K such that you can also upper bound it by OPT of T. Okay. Say again? Right. So let me say that I'm maximizing here over unitary matrices. When the unitary matrix is diagonal, it means that on the diagonal you have plus minus 1s. That's a generalization. So basically, you take a bilinear form that only involves the diagonals. Okay, so this bilinear form can just take some combination of the diagonals of A and B, and that reduces to this case here. Okay, this is why generalization thinks. And Grothendieck conjecture, the same connection holds. The SDP here, I don't want to write it down. It's not very difficult. Basically, what you do, as before, you replace scalars, like plus minus 1 before, by vectors. So the scalars here are the entries, those entries of the matrix A. And so here, instead of having a scalar valued matrix, you have a matrix whose entries are vectors, not unit vectors. And then you need some constraint that expresses the fact that the matrix is unitary. So you have to say what it means for a vector valued matrix to be unitary. And actually, it turns out there's a very nice way of doing it. You have to say something about norms of rows, norms of columns. And it's amazing that it works. It really works nicely. So this SDP is quite beautiful when you get used to it. Let me not go into that. So this was conjectured by Grothendieck in 1953. It took a long time to prove, and this was actually finally done by Pizier. Pizier proved it in 78. He proved that that missing part of the inequality, and the constant was later improved by Hagerup. Also gave slightly nicer proof. This was Hager group 85, and he managed to prove it with a constant k equals 2. Okay. So it's not much worse than the special case. And turns out, surprisingly, this was proved by Hager group and Ito in 95, so a decade later. This is tight. So there are examples of bilinear forms. There are examples of such T's where there's a gap of 2 between these two things. This is twice as big as that. Okay. We'll get back to that tight example later. Okay. So this is what in computer science we call integrality gap. We have examples where SDP is bigger than the OPT by a factor of 2 in this case. Okay, so questions? So this is where things stood. And then last year we had a paper with Asaf and Thomas Vidic from Caltech, where we said, kind of went to this inequality and started asking ourselves, is it interesting? Is this inequality interesting, or is it just some abstract nonsense? It's definitely interesting for people like doing people in math, but is it interesting for us? And we were surprised to find out that, yeah, it is. We found out that OPT is actually interesting. It has interesting applications, maybe even more so, would dare say even more so than the commutative case. So it turned out there are optimization problems people looked at, things like it's called robust PCA, robust principal component analysis, actually 2 versions of it, and something called the Procrustes version, Procrustes problem. This is saying that things that people looked at, and this turns out to capture. Actually, Amit Zinger and Afonso Bandeira looked at this, such related questions in connection with some tomography questions that they have. The reason this is interesting, because you can optimize over rotations. So you can, what they have in their project, they have certain pictures of molecules and trying to align them together. This is the kind of thing that you can capture here. Okay, so this is the first thing we noticed. This is actually an interesting optimization problem. There are some bilinear forms here that lead to interesting questions. And then we note as well, SDP is an SDP, is a semi-definite programming. So you can efficiently compute that. Okay, maybe slightly less obvious. I mean, at least if you stare the definition of that, in papers, in previous papers, it's not immediately obvious, but it is a semi-definite programming. And finally, we mentioned to do algorithmic rounding. Algorithmic rounding. Basically, we noticed that we just observed that Hager groups proof from 85 can be made algorithmic. There's a procedure that takes a vector solution here and outputs matrices through unitary matrices. It's a very nice algorithmic, a very nice rounding procedure due to Hager group, right? We just noticed that it's algorithmic. It's a very nice, unusual, I would say, rounding procedure. You do some randomized rounding, use some random projection, and then you have to carefully round the matrix to a unitary matrix. But again, this is not the topic of today's talk. It will become all very explicit in a minute. So, questions so far before I start discussing hardness? Yes? Yeah, so there's a lower bound, I forget, like 1.6 something. I forget what the exact lower bound is. I'll mention it in a minute. So hardness. So naturally, in computer science, we see an optimization problem, and we want to figure out how well can we approximate it. This approach, the semi-definite programming, gives us tells us that you can approximate within 1.782, but can we do better than that? Can we prove hardness results? Okay, and this is reasonably well understood for the usual case, for the standard Grothendieck. Okay, before this matrix stuff, it's reasonably well understood, I would say. So there's work by Cott and O'Donnell, who basically showed this hardness. This comes from the best known lower bound on the constant kg. This is Cott O'Donnell in 09. And there's another nice work by Raghavendra and Steuer, and same year. And they showed something funny. They showed that, the hardness of this is exactly kg. The hardness of this problem is exactly kg. even though we don't know kg. So there's some kind of generic argument saying that whatever kg is, we have hardness up to that kg. So good, and so this is kg factor, and this is all under the unique games conjecture. Okay, both these things were under the unique games conjecture. And I should say that maybe you can make it also under NP hardness. I'll maybe mention it later. I don't know. I didn't try. At least one, maybe they call it Donald. But again, I didn't try, so I don't want to say. I'll mention it in a minute. So this is reasonably well understood, maybe apart from the fact that it's based on unique games hardness. And what we were trying to figure out is what happens in the non-commutative case. No, good. Ask. Yeah.
Yeah, what does it mean?
So it means that there cannot be any algorithm that provides a better approximation factor than kg, meaning there's no algorithm that can take such an m and output a number that is within a smaller factor than kg of this true maximum, unless something bad happens in complexity. There's no efficient algorithm that can do that. There's no polynomial time algorithm, right?
The usual hardness result says that if you had a polynomial algorithm, then P would equal NP. And here, if you had a polynomial time algorithm, you would not be able to solve any complete problem, but this particular problem, which is pretty important.
Yeah, so what we'll do today is based on the usual assumption that P not equals NP. We'll show that if you can approximate better than something, you can actually prove, you can get that P equals NP. This is not as strong. This is actually a big open question now, whether unique games conjecture holds or not. What I said briefly before is that it's possible you can, maybe using some new technology, turn this into a true NP hardness result based on P not equal NP, but I don't know. We were trying to consider the non-commutative case, and pretty much nothing was known here. Exactly, except what comes from this. So this is as hard as this. So you get, at least, what you get from commutative. So it's at least 1.4 or something. The reason it's a small number is because this is the complex case. So here I'm discussing the complex case, and what is known for the complex standard Grothendieck is 1.4. Okay, so it's not 1.7, but. So basically nothing was known except what you get from the fact that the commutative case is a special case. Okay, so there's nothing specifically known for this. And this is what we want to prove. And the main theorem is this. So this is our theorem. And basically we say that for all epsilon bigger than 0, approximating NCG to within 2 minus epsilon is NP hard. So this is what we call a tight hardness result, because we know we can approximate it to within 2. This is what I mentioned before. This is a result of Hagerup, that SDP and opt are within a factor of 2. Okay, so we can efficiently, polynomial time algorithm, approximate this OPT to within a factor 2. And turns out even 1.9999 is already NP hard. You cannot do that. This is what I'd like to prove today. And just for those not familiar with the CS language, very soon become all mathematical. So I won't mention NP hardness from 5 minutes. So this is the main theorem. Let's call it theorem 1. And actually, what we'll prove is something stronger. We'll prove something stronger. This is theorem 2, that for all epsilon bigger than 0, approximating the little non-commutative Grothendieck is NP hard. To within square root 2 minus epsilon. So little non-commutative Grothendieck, Grothendieck gets lots of adjectives. But little non-commutative Grothendieck is a special case of this. Okay? So if we prove that the special case is hard, we also get that this is hard. And it just so happens that the translation involves a square. So if you have an approximation of this to within 1.99, you immediately get here an approximation to within square root of 1.99. That's what it is, square root 2, not a 2. So we actually prove something stronger, that this is already NP hard. Okay. So just so we can get to the mathematical part, the more interesting stuff. Let me start with the warm-up. And the warm-up will be to do that for the standard Grothendieck case. Okay, so before we do matrices or anything scary, let's just start with the standard case of Grothendieck. Let me tell you how we actually prove hardness result there. So this is what we'll start with. This is the warm-up. And we'll do this for all epsilon bigger than 0, approximating little Grothendieck. Not the non-commutative version, but the standard problem of Grothendieck. So I'll define in a minute what I mean by little Grothendieck. It's a nice problem. To within square root of pi over 2 minus epsilon is NP hard. Okay. And the nice thing, actually, this is tight. This is tight. For the special case of little Grothendieck, we know exactly the right approximation factor. I'll mention in a minute what little Grothendieck is. So this is tight, and we show a tight NP hardness result. I should say this was previously known. This result was previously known, but under a stronger assumption, under the unique games conjecture, not under the P not equal NP, but under this unique games conjecture that we mentioned before. So this was previously known under UGC by Cott and Naor. So Cott and Naor, 09, proved under UGC. Okay. So let me tell you what little Grothendieck is about. It's actually a kind of cleaner, simpler problem than the original Grothendieck. And it says the following. So little Grothendieck. So you're given a matrix B, given a matrix B, you want to compute what I would call the norm of B as an operator from 2 to 1, from L2 to L1. So I want to compute this, the norm of B from L2 to L1. And that's simply defined as the maximum of Bx in the 1 norm over all x of 2 norm 1. Okay, so let's pause for a minute. Let's try to understand what this is. So I claim this is actually a somewhat natural optimization problem, and it asks you the following. So you're given a matrix. You're trying to compute or approximate this maximum here. But if you stare at this for a minute, you notice the following. So, well, x here ranges over like a sphere, all vectors of unit norm of norm 1. And so what is Bx? You apply a linear transformation to it. So you might think of Bx as being some ellipsoid. And basically what you're doing here, you're maximizing the L1 norm in an ellipsoid. This is the question. Okay, trying to find the point of largest L1 norm in an ellipsoid. So this is a little Grothendieck problem. And turns out, as I said, this is a special case of the standard Grothendieck problem. And I'll show you why. It's easy. It's relatively easy to see why. Okay, so is this okay? Yes. Okay. So let me try to rewrite this in a way that will show you why it's a special case. So here we have a maximization of the L1 norm of Bx. So I'll just notice that you can express the L1 norm as the maximum in a product with a vector of L infinity norm 1. Because what is L1 norm? It's sum of absolute values. Okay, that's like taking in a product with the best choice of signs for the vector. So I claim that this is the same as maximum of y transpose Bx, where x is vector of L2 norm 1, as before, but now I have y of L infinity norm 1. Okay, so this is, so far, shouldn't be very surprising. You can always express the L1 norm, which is sum of absolute values, as the inner product with the best choice of signs, with the best vector of L infinity norm 1. And now I kind of go backwards. I'll notice that, well, what does it mean to maximize y transpose Bx over all x of L2 norm 1? Well, that's exactly the L2 norm of y transpose B. Okay, if you just think of it this, by Cauchy-Schwarz, this is exactly the maximum of y transpose b in 2 norm, and we're taking maximum of all y of n infinity norm 1. So what I did so far is one of the most basic facts in function analysis. I just told you that the 2-to-1 norm of b, or generally the norm of an operator, is the same as the norm of its adjoint. So the adjoint of b would go from the dual of 1, which is n infinity, to the dual of 2, which is also 2. So this is all I did now. What I did here, just notice, this is just the norm of the adjoint b from infinity to 2. And actually, so this is just terminology. The nice thing, if you stare at this, it also has a nice interpretation. You have a matrix B, and you're trying to find the kind of plus minus 1 combination of the rows has the biggest L2 norm. Okay, another question that you might encounter once in a while. Okay, so you can get a matrix B, trying to find a combination. Y has plus minus 1 entries, combination of rows that gives you the maximum L2 norm. Cool. So far I didn't do much, and now comes the actual step that I need to do. So I'll just express the 2 norm as the inner product with itself square root. So just write this as y transpose b, b transpose y to the power 1/2. And again, over all y of n infinity norm 1. And turns out, to complete the proof, turns out I can equally weight maximizes over y and z of n infinity norm 1 of y transpose b, b transpose z to the power 1/2. Because of Cauchy-Schwarz, because this BB transpose is positive semi-definite. So let's see why. I just told you that I can allow these two vectors to be arbitrary. They don't have to be the same, and it doesn't change the value. It's still equality. And this is simply Cauchy-Schwarz, because take an assignment. So obviously, this is at most that. Okay, I have more freedom here to do the reverse direction. Take any assignment here, any y and z, and just use Cauchy-Schwarz to notice that this is bound by y transpose b, b transpose y. Okay, this will be one side of Cauchy-Schwarz, and z transpose b, b transpose z. So basically, you get two such expressions, one for y, one for z, and you get the geometric average of the two. So one of them must be bigger than that.
I don't think you need PSP. I think symmetry is enough to have to solve for effect. Just the fact that BB transpose is symmetric.
Don't think so. You can take for instance, well, then you maybe need absolute values, but yeah, I think, yeah. No, I think we need positive semi-definite. Yeah. Symmetry is a very weak one. You can always assume it's symmetric. In the Grothendieck problem, if it's symmetric, it doesn't buy you much. It's because you can always turn the matrix into symmetric by just, yeah. Okay, we can think about it later. It's either, the obviously true, obviously false, but I think symmetry is not enough. Okay, so just to summarize so far, all I told you is this is what we want to care about, this problem of computing the norm of an operator from L2 to L1. Okay, this is the little Grothendieck problem, and I showed you why it's a special case of the usual Grothendieck. So now all we have to do is just show why this is NP-hard to approximate to within square root pi over 2 minus epsilon, and see where the square root pi over 2 comes from. And it's actually, the proof involves, I don't know if you've seen NP-hardness proof before. I will not torture you with this whole machinery of proving NP-hardness results. Turns out there's established machinery how to do such things. And what we end up using, so if you're willing to use the unique games conjecture, it's even much easier. It's one of the easiest unique games hardness proof I know of. But if you want to prove NP-hardness like we do, you have to work a bit harder. So we end up using a nice way of kind of replacing unique games with NP-hardness for the expert. Let me just say, it's a nice result of Guruswamy, Raghavendra, Saket, and Wu from 2012, showing that sometimes you can avoid using unique games by using what's called smooth PCP. It's something that Subhash Kot did some years earlier. And sometimes the smooth PCP is like unique on average, and sometimes it's enough for you. But if you didn't get that, that's fine. So all I care about is that using this machinery, and we do a bit more work, you can reduce the question of hardness to the following mathematical question. Okay, finally we get to the mathematical content, and here's the thing we're trying to prove. And once we prove that, we have the hardness result. Okay, just take my word for it. This is the thing we want to prove. Okay, and this is the following statement, that for all n there is a function, or actually linear operator, from Rn to L1. I use capital L1 because I want to think of it as a function, but if you're not comfortable, think of it as little L1. So we have a function that maps n-dimensional vectors to L1 with the following property. So two properties, two very simple properties. So the first thing is that for all I, if I take f of the standard basis vector ei, so the standard basis vectors are mapped to things of L1 norm 1. Okay? Very simple. Standard basis vectors, norm 1. The second thing I need, and this is the last one, is that for all A, if the L1 norm you get is bigger than, say, 2 over pi plus epsilon times the L2 norm of A itself, then A is not smooth. A has some peaks, has some values where it's big. So the n infinity of A is bigger than some epsilon, some epsilon, maybe epsilon over 10 of the L2 norm of A. So let me just say what it means in words. I need the following conditions. First, I need standard basis vectors to be of norm 1. And the second condition is that if there's no big coordinate, if you think of the vectors being relatively smooth, no one coordinate is too big, no one coordinate is bigger than epsilon, then I want the norm to be square root 2 over pi, roughly. Okay. So typical vectors, almost all the vectors get norm square root 2 over pi, but I want the standard basis vectors to get higher norm, to get some preference, to get norm 1. Okay. Turns out once you have this, you can plug it into this machinery of NP hardness and get NP hardness result. So what we need here is basically just a geometric statement saying that you can have such a mapping. If you wish, you can think of it as finding some subspace of L1 whose unit ball looks a bit like chopped sphere. So you take a sphere and kind of chop these parts of the sphere. This chopping effectively makes the norm of the standard basis vectors larger. Okay, if this is a unit ball, then the norm of a point here, of E1, or a point here, just increased because I chopped the unit ball. If you like this geometric intuition. I need you. Yeah.
The number 2 of pi can arise in a lot of ways, but I was wondering, like, if you take a unit vector, a relatively smooth unit vector A, and you take random signs in a part of the random signs.
Good. You can take over. You can take over. This is the proof. Yeah. Good. Great. Thanks. So this is really the proof of the lab. And actually, the mapping is very simple. Okay. This is the point I'm trying to make. So you already managed to get the hardness for the little Grothendieck statement. So the proof is simply that. Let me show you the statement, the mapping. So the mapping is this. I have a mapping of f from Rn to L1, so functions on -1, 1 to the n. And the way the mapping works, I take a vector A, and I map it to the following function, or if you wish, like a vector of dimension 2 to the n, that takes sine z1 up to zn, and maps them to sum of ai zi. Okay, so this is the linear operator I want to consider. And basically all I'm doing is just taking a random ±1 combination of the coordinates of the vector A. And no, nothing. Yeah, because it's going to be implied in a constant, yeah, it's the inner PCP. So it's going to be, I only care about.
Wouldn't it be okay if you replace all the possible patterns, sign patterns just by an epsilon bias family?
Yeah, so you can do, I think, yeah, you can probably do 4 Ys is enough, yeah. Then it's not even efficient in that sense. Yeah, I think we mentioned it. Thanks. So the norm, by definition, the L1 norm we care about of f of a is just the expectation of the absolute value of sum ai zi, where zi are the signs, expectation over the sign zi. And if you stare this, so if this immediately implies that, well, 1 holds. The condition 1 holds there, because if this is a standard unit vector, so there's only one coordinate that's 1, all the others are 0, the distribution you get here looks like that. I mean, this is 0, this is 1, this is -1. It has, probability half it's 1, probability half it's -1, and the expectation of this is 1. Expectation of the absolute value is 1. On the other hand, if you have lots of small coordinates, so, central limit theorem, or in this case, the Berry-Seen theorem, tells you that you're going to get something that looks like a normal variable. And as Anidia knows, the expectation of the absolute value of a normal variable is square root 2 over pi. Okay, so if there are no big coordinates, you kind of things to try to cancel, and you get this nice normal distribution. The variance is the same. The variance is always 1. Or I should say maybe the norm of A. This is the standard deviation. But turns out that the absolute value changes. So if you just do the computation, it's a very easy integral. You see that this has a smaller L1 moment, first moment than this. Okay?
This mapping was not used in other...
So the thing in Grothendieck, they try to do something more general, and I think it's there. I think it's in there. It's just hard to actually dig it from the proof. So there was, for some reason, they used all this machinery of majority tables, and we don't need any of this. Surprisingly, the proof doesn't use any of this modern machinery, which is nice. But yeah, I don't think, I'm sure, this has been used in tons of places, right? This is pinching inequalities all over the place. People use that. The property of the Gaussian. So this is just a warm-up, and what we actually need for our proof is a similar thing for matrices, okay, not for vectors, and this is what I'll try to briefly tell you how we do. And so we need to prove the same lemma, except now, again, this is for the non-commutative case. We need to put an S instead of an L. I'll tell you what this is in a minute. So here I should put an S, I guess, and here. So I'm just changing this and here. And the only other change I need is that 2 over pi now becomes 1 over square root 2. Okay? Yeah. So this is the same thing we need to prove. Okay. Same thing, different constants. This makes it harder to prove, right? Because this is a smaller number, 1 over square root 2. And we need to prove it for something else called the S1. So what is S1? S1 is the matrix analog of L1. So S1 are matrices with what's known as the Schatten-1 norm. That's why I call it 1. And let me just define it. So A S1 is defined as D. So A is a D by D matrix. And define the S1 norm as basically the average of the singular values. If you know what singular values are, it's basically the average of singular values. And there's a nice way of writing it. I know you all miss linear algebra, so let me remind you of some linear algebra. Okay, this is basically the average of singular values. Okay. So singular values, you can think of it as, like in the case of a normal matrix or a symmetric matrix, you can just simply the absolute value of this eigenvalues. But this is defined for any matrix A, and we take the average and the L1 norm of those singular values. So, and in case the matrix is diagonal, this is simply the L1 norm of the diagonal. Okay, this is why it's an extension of the L1 norm. Diagonal matrices, this gives us L1 norm. Generally, it gives us something more interesting called the S1 norm, the Schatten-1 norm. Sometimes called the trace norm. It is used a lot in, say, quantum information. This is the statistical distance in quantum. Instead of L1, you do S1. What we call the variational distance. Okay, so how do you approach this? I mean, we got to that point, and we thought, okay, where do you find such a mapping, right? Previously, we just used Bernoulli's, and it was easy to understand. And we're kind of wondering, what would be the right analog here? How do we... Right, unitaries make sense because unitaries kind of maximize, maximize all the singular values of 1. So we would like to use unitaries. And the first thing we try to do is maybe use random unitaries. We're hoping random unitaries have a nice structure, maybe better cancellations than we get from Bernoulli's. And we thought this has to work. It doesn't seem like it works, actually. It seems to give something worse than what you get in the commutative case. And if you imagine you take a kind of random combination of random unitary matrices, what you start getting is known as the Gaussian ensemble. So it's a distribution random matrices whose entries are Gaussian. And turns out this matrix, due to well-known facts, such matrices have very nice shape, very nice distribution of eigenvalues. It's called this Wigner's semicircular. Very nice distribution that looks like that, all between 2 and -2. It's something that's been investigated for many years. It's a beautiful property. And you compute it, you see that actually with such matrices you get a much worse gap. It's like instead of being 1/√2, you get it's like 0.88 or something. In some sense, random matrices tend to be kind of more concentrated than random vectors. Okay, so I'm not going to talk too much about this. This seemed like a dead end. I think we tried that too. We considered that, and I think it would also lead my intuition would also lead to something like that. But kind of. So then we say, okay. So what we often do in such cases. First, let's check out the integrality gap. Okay, let's check out where the integrality gap. This Hagerup Ito paper. Let's see how they did it. How they show the case where SDP is much bigger. Maybe we can extract from it Hardness result. This often happens in computer science, in such questions. And turns out also I should say that this example here really comes from this construction from the commutative case comes from the integrality gap. And integrality gap is similar, except you map vector A to sum of AI GI. GI are IID Gaussians, okay, not Bernoulli's. This embedding, this function turns out to be an isometric embedding. It turns out that you take the L1 norm of this. If you use this mapping instead, the L1 norm of this is exactly the L2 norm of A. Okay, this is an isometric embedding. And basically what I guess Kotner did here is introduce some impurities. Instead of getting a Gaussian, you take Bernoulli, and Bernoulli favors the direction of the standard axis, standard basis vectors, right? If you have a vector that has no big coordinates, those Bernoullis mix and start looking like Gaussians, but the Bernoullis themselves have some preferred direction. So what we did here is went to Hagerup and Ito's paper to see how they did it. Okay, smart people, we should see how they do it. And turns out what they use is something called the CAR algebra. Okay, so it's called canonical anti-commutation relations. It's something that probably people doing physics know, do it for breakfast. CAR algebra, this is what they used. And what this gives them is basically some analog of those Gaussians. So this gives some interesting matrices that give them this isometric embedding of L1 into the space of L2 into the space of S1. So it's an isometric embedding, namely there's no preferred directions. This is what they do there. This is in the Hagerup Ito. So 95. And at the bottom line is this turned out to be a dead end. We still don't fully know how to use this. Instead, we end up using a different algebra. And sometimes you do research, you have to work really hard. What happened here is that we were just extremely lucky, I think. It turns out that there's another algebra known as the Clifford algebra. And turned out that when you use it, everything works perfectly. So we really got more lucky than we should, I think. And turns out that the Clifford algebra works perfectly here. I'll tell you a bit about this Clifford algebra. I should say this Clifford algebra has been used a lot in quantum information. It's connected to something called Tsereson's inequalities, Bell's inequalities. So I'll tell you what this is. So the CR algebra that they used gives you isometric embedding of Cn into L1 and S1. What the Clifford algebra gives you is also an isometric embedding, but it's of Rn into S1. So it seems bad because it just maps isometrically Rn into S1. Okay? It doesn't have any preferred direction. This is why it's so useful in quantum information, among other things. And what we realized is that if you just try to feed into it complex numbers, suddenly some magic happens, and which we still don't fully understand. I'm sure this was what we do here is something that's known to mathematicians in the 19th century. We're not doing anything sophisticated. We're just saying, take this Clifford algebra, the generators of the Clifford algebra, and take a linear combination with complex coefficients, and then some magic happens. Okay, I'll show what the magic is, and this is something that I'm sure some mathematicians sometime in history figure out. We couldn't find a reference. We asked a few people, but it's some use of the complex complex Clifford algebra or something along this line. Okay, we're not experts in this. So I don't know. I wouldn't even know how to properly phrase this. But here's what we prove. Okay.
What would happen if you just use the basis of the Clifford algebra, the plus minus? I mean, the matrix.
That's what we do. Yeah.
Oh,
Yeah. Yeah, we take a generator, not the whole algebra. Yeah. Yeah. Just a generator. Right. Good. Yeah. Yeah. But somehow, yeah. So let me show what we noticed. This is a lemma, and this is. If you are familiar with this lemma, it's just a calculation. You have to just do the calculation. It's not very difficult. So we have a mapping. This is what we do using this Clifford algebra. A mapping from Cn into Cd times D by T matrices, such that for all A in Cn, so you take any vector A and you apply this mapping C, you get the following norm as the output. So the S1 norm of this happens to be the following expression. Looks a bit scary, but it's actually a very nice expression. N2 squared plus lambda of A plus 1/2 square root of L2 squared minus lambda of A, where lambda of A is the area of the parallelogram formed by the real part of A and the imaginary part of A. Okay, so let's see why this is enough to complete the proof. So this is just a calculation. Okay, you do some linear algebra magic, nothing very deep, and you get this is exactly the S1 norm of this mapping here. And the mapping, as I hinted at, the mapping simply takes A, so C takes A and maps it to a sum of AI, CI, and C are those generators of the Clifford algebra. Those are simply anti-commuting, symmetric anti-commuting matrices. Okay. Let's just see why this completes the proof. Imagine that A is a unit vector. Okay. Sorry. Say again? No. Nothing. So far, there's nothing random. These CIs are really explicit. I can write the matrices. So, you can exactly write the matrices. Good question. Yeah, there'll be something random. But in a sense, the randomness is kind of replaced by the. So there'll be an extra randomness. But I think also there it was not really random in the sense that you can imagine this is a deterministic function that like a vector of dimension 2 to the n. This is one way of viewing it. And here I have a matrix of dimension 2 to the n by 2 to the n. But you're right, there'll be extra randomness in a minute. Okay. I thought of it in a random way. I wrote it in a random language, but you can think of f as mapping an n-dimensional vector to a vector of dimension 2 to the n, period. Okay, no randomness. It's just a linear mapping. But it's convenient to think of it in a random way. And here we have something mapping to matrices. And let's just see the calculation. Let's plug in here. So imagine I want to compute C of EI. Okay, EI is a standard basis vector. So, well, this norm is 1. This norm is also 1. So what is that? What is the parallelogram formed by the real part and the imaginary part? 0, because the imaginary part is 0. Okay, so this part is 0. And what I end up getting is simply 1. Okay, good. This looks good. This is what we needed. But actually, if you think of it for a minute, you actually see that the same, we didn't use the fact that it's EI. The same would be true for any unit vector. So in fact, for all A in Rn, if the norm is 1, the norm of CA is also 1. Okay. This is kind of bad, right? We wanted to distinguish between vectors that are peaked, like EI, like standard basis vectors, vectors that are smooth. And it doesn't work. And that's not a coincidence. I told you before that this Clifford algebra is usually the way it's used is a mapping from Rn. And there it's isometric. There it maps anything of unit norm to something of unit norm. It maps 1 to 1. However, and this is where these correction terms come in, here's the idea. Imagine you have a vector that has no b coordinates. So imagine, say A is the vector 1 over 10, 1 over 10, like 100 times. Okay. So, if you just take C of A, you're not good because this has norm 1. We want the norm to be smaller. Turns out what you can do is imagine what you do is this. Pick. Exactly. So you want to multiply, well, yeah, you could do it just coordinate by coordinate. Because I want to keep the standard basis vectors. Yeah, good. So just take omega chosen randomly from all 4 to the n possible choice of signs. 100, also 100 here. So I take omega to be a vector of phases, plus minus 1 or plus minus I. I is the complex I. And then if you think of A times omega, and point-wise product, you get, maybe the first coordinate is minus 1 over 10, then you get I over 10, then you get minus I over 10. You get some random phases, either plus, minus, or I or minus I. And why is that so nice? Because now if you consider C of this vector, I claim that this is roughly 1 over square root 2. And let's see why. Because now if you consider this parallelogram formed by the real part and the imaginary part, those are now orthogonal. Because half of the coordinates will contribute to the real part and the other half to the imaginary part. So we have, in this vector, half of the coordinates are in the real part, the imaginary part is the other half, so they're orthogonal. This means that the area is the product of the two lengths, and each one is of length 1 over square root 2, roughly, because there's no big coordinates, so we kind of split them half. So we get that the area is half. It's 1 over square root 2 times 1 over square root 2. So it's half. I think so. No, did I do it wrong? I did it wrong. Yeah, so what do you want to say? Did I do it wrong? Yeah. What did I do wrong? Oh, yeah, I've got 2. Sorry about that. Much better. OK, so there's a 2 here. So the area is half, and now this gives me 1. This 2 lambda is 1. So in the first square root, I get 1 plus 1 square root. So it's square root 2 divided by 2, 1 over square root 2. This gives me 1 minus 1. So this is 0. So to summarize, the construction we use is the following. Okay, we use this mapping C, but not apply it as is, because if we just apply it as is, it won't work. It's an isometric embedding. So before applying it, we take our vector A, multiply it by some random signs, and then apply C. Okay, that guarantees that if A is kind of smooth, has no big coordinates, we'll have those cancellations happening, and the norm will end up being 1 over square root 2, and not 1. Okay, this is exactly what we want. We have this gap between 1 and 1 over square root 2. And I should mention that multiplying by those phases doesn't hurt the EI. So you can multiply this by, well, sorry about the I. This is a different I, of course. But if we multiply it by like I here, which is a different I, complex I, this doesn't change. The norm is still 1. Okay, so standard basis vectors are mapped to 1. Smooth vectors map to 1 over square root 2.
So every coordinate you choose 1 of 1 minus 1 plus I.
Correct. Independently. Every coordinate, yeah. So, yeah. You might be worried about the order of quantifiers here, because we want something that holds for all A, no matter what choice of omega you do, but that's fine because we actually take all omegas together and average over them. So the mapping is actually not the C, but rather a direct sum of all 4 to the n possible C's, if that worries you. Okay, that's a final mapping. So just to give you something to think about, if you want to explore this more, let me just say that what are those CIs? I don't want you to think it's mysterious. It's actually something, it's all very explicit. So all you need the CIs to be, so this C1 up to Cn, those have to be anti-commuting anti-commuting symmetric